Kamiak Butte is located in the hills of the Palouse region of eastern Washington. It is an ancient site created by tectonic activities and fissure eruptions that happened millions of years ago. This laid the foundation for the site, but now the biome is impacted by other forces, such as climate, solar radiation, plant and animal interactions, as well as human influence on this beautiful site. In this presentation, we will dive into the complexities of this biome. The formation of eastern Washington began about 70 million years ago, when the continent started to resemble its current state in the world, including the North American continent. During this time, the oceanic crust was subducting underneath the continental plate, forming an accretionary wedge along the then coastline of the plate. With the North American plate's continued shift west, it came in contact with the Juan de Fuca plate and caused the North American plate to shift upwards, causing parts of Washington to rise above sea level. Further contact with the Juan de Fuca plate increased volcanic activity due to subduction, causing the formation of the Cascade Mountains on the west coast of Washington. Eastern Washington is also impacted by large deposits of basalt rocks. Large fissure eruptions through vents on the boundary of the North American plate began about 17 million years ago. This created a large outpour of basalt that covers the majority of eastern Washington, known as the flood basalts. Flood basalts spread over 63,000 square miles, and in some areas, they are up to 2 miles thick. These fissure eruptions lasted for about 2 million years, during which 99% of the basalt was released. Kamiak Butte is surrounded by this basalt, and it's still easily visible today in the region. Above the thick flood basalts that cover eastern Washington stands the peak of an ancient mountain range. Before the flood basalts, about 150 million years ago, the land was made mostly of quartzite rock. This is what formed Kamiak Butte. These ancient mountain ranges were formed from heat and compression that caused sand-like rock that was once on the continent's coastline to metamorphose into hard quartz that formed large hills that were uplifted from tectonic movements we previously mentioned. Now only the head and shoulders of this mountain are visible above the thickness of the flood basalts in Kamiak Butte, located outside Pullman, Washington. Due to changes in the Earth's climate about 2.56 million years ago, the North American continent began to be covered in glaciers. These glaciers were about 1 kilometer thick and stretched to the edges of Washington, Idaho, and Montana, as seen in the graphic. These enormous glaciers began to melt about 17,000 years ago as the planet began to warm. The initial result was ancient Lake Missoula in Montana, a massive lake about 2,000 feet deep. This lake eventually overflowed and broke the ice dam that encased it, leading to a series of floods in the surrounding area. As the Ice Age ended, a cycle of heating and cooling of glaciers led to extensive flooding. Lake Missoula flooded back into the Clark Fork River, where pressure built up, eventually giving way and creating massive channels of water that scoured through the landscape and carving it. These massive glacial rivers ended in Wallula Gap at the beginning of the Columbia River. These massive floods eroded the landscape of eastern Washington. The glacial waters formed large U-shaped valleys across the state, carving underlying flood basalts. We can see evidence of this at sites like the channeled scablands, potholes, massive ripples across the landscape, and Palouse Falls. Kamiak Butte lies within the marine-modified continental macroclimate. The biome of Kamiak Butte is a unique combination of climatic factors like air mass, interaction with topography, and solar radiation. As stated previously, the tectonic activity created a unique topography at Kamiak Butte. While air masses from the Pacific Ocean moving west and Arctic polar masses moving south create weather patterns over the region. Rain shadows and solar radiation affect the plant life that can grow at Kamiak Butte, while we dive deeper into how only 100 meters can make the difference in this biome. The entire world's weather systems are impacted by air masses in the troposphere. The air mass that impacts the Palouse region is the marine polar air mass that forms over the Pacific and moves east into the northwest region of the continent. The marine polar air mass is full of moisture that it absorbs over the ocean and moves inland towards western Washington. However, these energy-packed clouds must ascend the Cascade Mountains, creating a rain shadow for eastern Washington and Kamiak Butte. During the winter months, the continental air mass and Arctic air mass move in the region, creating cold fronts and winter storms, causing up to 3 feet of snow in the Pullman area. This interaction of air masses causes dry, warm summers due to limited cloud cover, allowing the sun to directly warm the ground, and cold, precipitation-filled winters, when dense clouds from the Arctic polar system move in, causing increased precipitation and cold fronts. The topography that shapes the land can affect the biome that forms. As previously stated, Kamiak Butte is the peak of an ancient quartzite mountain. The topography of Kamiak Butte impacts the biome of the mountain. The south-facing aspect is about 3,400 feet in elevation and has a steep slope that directly faces the sun. The north-facing aspect is about 2,900 feet in elevation and has a gentler slope towards the peak of the mountain. These factors can impact the biome's plant and animal interactions as well as phenology. Eastern Washington's climate system is affected by a rain shadow formed by large mountains on the west side known as the Cascade Mountain Range, which clouds have to travel over, losing energy as they do and decreasing overall precipitation in this region. The rain shadow starts when the air mass cools over land and precipitates up to 12 feet of rain in the Olympic rainforest, unloading much of the moisture that the system absorbed over the Pacific Ocean. The air mass then travels east, reaching the Cascades, where it's uplifted thousands of feet towards the mountain's peaks, losing energy but gaining water vapor that precipitates over the mountains. After losing energy and moisture, the clouds descend to lower elevations, where the clouds warm and continue to travel east, unloading minimum amounts of precipitation in this region. This is known as the rain shadow. This phenomenon causes limited precipitation in the area during the summer months, as well as increased temperatures due to limited cloud cover. The amount of sunlight an area receives can directly affect the characteristics of a biome. In Kamiak Butte, the south-facing aspect of the mountain is exposed to direct sunlight for most of the spring and summer, making it very hot and dry. Increased temperatures and limited moisture on the south aspect only allow ponderosa pine trees to sparsely grow, as it can survive with limited moisture due to competition with other plants for water and nutrients. While the north-facing aspect of the butte appears very different since it receives less photosynthetic active radiation from the sun, more moisture is present and allows trees to germinate and grow in the dense area as well as other plant life in the understory. This chart demonstrates the influence of the factors mentioned, such as air masses, topography, and rain shadows, as well as solar radiation and how they affect the climate in the region. The rain shadow created by the Cascade Mountain ranges decreases overall precipitation received in the region. Most of the precipitation comes in the fall and winter months when Arctic polar, continental polar, and marine polar air masses interact. This climate pattern often leads to wildfires during the summer months because temperatures are high and winds are amplified, and moisture is low, causing brush fire to ravage the areas in the region. Conversely, this also leads to winter storms and cold fronts in the region due to high levels of precipitation received during these months. One factor that makes Kamiak Butte so unique is the underlying substrate. This differentiates it from the larger western interior shrublands and woodlands biome. In previous slides, we talked about how this substrate was created. The loess soil is nutrient-rich and can retain water easily. This allows plant life to grow, while the quartzite substrate creates a different environment. It allows larger plants, such as trees, to plant deep roots into the ground. The south side of the butte directly faces the sun during the spring and summer months, which causes it to receive more photosynthetic active radiation. This can increase temperatures and create a drought-like stress on plants. The plant life on the south-facing aspect competes for resources such as water and nutrients, limiting the amount of life that can be supported, creating a more shrub-like biome. However, ponderosa pine trees can grow due to their ability to withstand limited water and increased temperatures. Grasses such as Idaho fescue, blue bunch wheatgrass, and North African grass creates an ecosystem for small game such as turkey, birds, and mule deers that can navigate more rocky terrain on the south-facing aspect. The topography of Kamiak Butte leads to a stark difference in the biome. The north-facing aspect is at a lower elevation and receives less photosynthetic active radiation from the sun, leading to more moisture in the area. This allows plants to germinate and grow with a substantial amount of water. The north-facing aspect also has increased primary productivity. The understory of plants gets consumed by herbivores that then can get consumed by predators in the area, and detritivores can recycle their nutrients into the abiotic environment, providing nutrients for plants and trees to grow successfully. The north-facing aspect has more dense plant life in the understory, such as elk sage, that support autotrophic animals such as white-tailed deer and moose in the area. Ungulates support apex predators such as cougars that hunt the deer, controlling their populations and providing a service in the ecological food web. With more biodiversity on the north side, it allows the tridivores to recycle the organic materials of dead plants and animals back into the abiotic soil, giving nutrients to plants and trees, while similar interactions occur on the south-facing aspect of the butte, but with smaller game and less nutrients being recycled back into the environment. Now we can take a look at carbon sequestration that takes place on Kamiak Butte. The process of carbon sequestration created by trees begins with nitrogen and chloroplast. Although nitrogen is the most abundant gas in the atmosphere, none of it is available to plants. They must obtain it from organic compounds in the soil that is retrieved through root systems and then goes to create and maintain the plant's chloroplast. Plant chloroplasts are responsible for photosynthesis that gives the plants energy when carbon dioxide and water is activated by solar radiation to form glucose. CO2 is needed to create glucose in this process, and oxygen is expelled as a waste product. This is how carbon is sequestered into plant mass. The north-facing aspect has a larger abundance of tall trees and of multiple species, including Douglas fir, western larch, and ponderosa pine. Height is an important factor in carbon sequestration because 80% of carbon is stored in stem root and foliage. Thus combined, the taller tree is more available space for carbon storage. The north-facing aspect of the butte sequesters much more carbon due to height and abundance of trees. As you can see in this table, the amount of trees per acre and the height of the trees on the north-facing aspect sequesters significantly more carbon than the south-facing aspect. The overall success of the mighty Douglas fir sequesters about 17.5 million pounds of atmospheric carbon. With the help of western larch and ponderosa pine, it captures a grand total of 18.5 million pounds of carbon. With only 35 trees per acre that are not able to grow as tall due to limited resources, the south-facing aspect only sequesters 700,000 pounds of carbon. Through this presentation, we saw how factors such as ancient geologic activities, climate, and ecology all play a part in the creation of the biome that is Kamiak Butte. From plate tectonics and climate patterns to phenology and carbon sequestration, the butte is a good example of the complexities that make up a biome.